Hello, everyone. Good morning, good afternoon. Thank you for being with us again for the new event of the Hypatia Colloquium. My name is Giacomo Beccari, and I'm very happy to, first of all, to welcome all of you, and I will never stop to congratulate with the speakers, with the speakers of today, and with all the speakers who passed through the challenging selection process and are making this event so enjoyable and so exciting. We are very excited about this, and to hear so the impressive amount of science that is done by the early career astronomer. It's in Europe and everywhere in the world. So we are very, very happy about this. So just today, the event will be co-chaired by Michele Ginolfi, who is a fellow at ESO, and who I would like to thank again for helping us. And I will be helping Michele for the second talk of the day. Just very, very quickly, there are some technicalities that you probably already are familiar with this, but basically the way to which the seminar can be followed is either through Zoom, and so people in Zoom can make the questions to the speakers once the talk is finished. The chair will give you the floor if you use the raise hand button that you have in Zoom, or and then you will be basically you can make the question yourself to the speakers. The ones who are following, people who are following the talk on YouTube are also very welcome to post the comments and questions all the time, basically all the time, using the live chat and on YouTube. And alternatively, they can be also, in case people who doesn't want, because you don't have a Google account or a YouTube account, then you can still send your question by using the questionnaire that is available online on our web pages, Hypatia web pages at ESO. Having said that, I think this is done. This is everything. So I will be very happy to ask Michele to please, you can start by introducing the first speaker of today. Ciao, Michele. Nice to see you. and we see each other later.
Yeah. Giacomo for presenting this. So yeah, welcome everybody. And it's my pleasure to present Yoshi Fudamoto, which is our first speaker. Yoshi did his PhD in Geneva, where I had the pleasure of working with him and reduced together a lot of data. Is now a postdoc at Waseda University in Tokyo, Japan. Yoshi is an expert on observational studies of Earth-shaped galaxies, mostly focusing on ALMA observation, on the properties of dust and the fraction of obscured star formation. And today he's going to talk about a panchromatic view of galaxy build up in the first 2 gigayears of cosmic history. So Yoshi, the floor is yours. I will stop sharing, and please, you can go ahead sharing your screen.
Thank you, Michele. I will start my talk now. I guess I think you can see my screen. So yeah,
yes.
Thank you, Michele, for inviting me this fantastic opportunity to talk about our recent results on the studies of panchromatic view of galaxy buildup in the Earth-shaped galaxies. So my name is Yoshinobu Fudamoto. I'm a postdoc working in National Astronomical Observatory of Japan, also in Waseda University. So today, I'd like to introduce our results based on the recent ALMA-Large program, for instance, first by the ALMA-Large program Alpine, and also another one is the ongoing ALMA-Large program Rebels. So let me start from the very basic overview of our understanding of galaxy evolutions. As we all know that sometime after the Big Bang, the first galaxy has been formed, and after that, and more galaxy has been formed and evolved into the galaxy, what we can see in the present-day universe. One of the main drivers of this galaxy evolution and formation is the star formation activity of galaxies. And to investigate and fully understand how this galaxy has been formed through this star formation activity, we will first need the complete census of star formation activity through the entire history of the universe. For this understanding, one of the very important ingredients is our understanding of dust attention property. the UV emissions typically emitted by the very massive stars, short-lived massive stars, which is the perfect indicator of instantaneous star formation activity within galaxies. However, this UV emission is typically what we observe is the dust-attenuated UV emission. This dust attenuation occurs in the dust particle by the scattering and dust absorptions of dust particle in the interstellar medium. And what we observe is the significantly altered emission from the original emission in the star formation site. Another important aspect of this dust particle is that after the absorption of these UV emissions, dust heats up. This emission heats up dust to the temperature of about a few times 10 Kelvin, and these dust start to emit the thermal emission in the far infrared wavelengths. So these dust particles really determine the entire spectral energy distributions of galaxies. So now the original emissions originated from this star formation activity is now split into two wavelengths range. One is Western UV wavelengths, and another is dust emission in far infrared wavelengths. So to recover the total emissions originally emitted by star formation activity, we will somehow need to correct this dust attenuations and take into account these also the dust emissions to get the total emission from the star formation activity. There's mainly two methods exist. One is the direct observation of both UV and infrared wavelengths. From UV observation, we will get that the dust unobscured star formation activity directly, and from the observations of infrared wavelengths, we will get the dust obscured star formation activity directly. So adding these both two components, we will get the total star formation activity of galaxies. However, apparent shortcoming of this method is that it takes a very long observational time. And also, especially sometimes these observations are not very sensitive to the galaxy at very high redshift. For instance, the relatively low sensitivity of existing telescope and also the existing data will not allow us to really determine the infrared luminosity of very high redshift galaxies at redshift, for instance, greater than 3. And also the recent very extreme sensitive interferometer such as ALMA will not still allow us to do the statistical study of these infrared emissions, because these interferometers typically have very small field of view. So another method would be the empirically estimate how these dust attenuate UV emissions and empirically calculate how this attenuated energy will be transmitted into the far infrared emissions. Then if we really understand how the dust attenuation occurs in the Western UV wavelengths, we can apply these dust attenuation rule to correct this dust attenuation to the UV observations. Because UV observation is sometimes more complete compared to the infrared observations, we can still use these UV observations even at a very high-risk universe. One such empirical relationship we can typically use is the so-called IRX beta relationship. So IRX beta relationship is very, very simple relationship which just connect the dust attenuation in Western UV and the dust re-emission in far infrared. Beta means UV spectral slope defined by the power law here, and IRX it means infrared excess, which is just a fraction of energy re-emitted by infrared and versus the UV. So this is just a dust attenuation in UV and dust re-emission for infrared. We can expect a very tight correlation between these two quantities. So indeed, the first study by Moyer 1999 shows that indeed there's a tight correlation between these two quantities, and found that there's the first established the calculated IRX beta relationship using local starburst galaxies. However, apparent very difficult situation is that because this dust attenuation property is purely empirical relationship, which this dust attenuation is a phenomena involving the dust extinction of each dust particle and also the geometry of between the stars and dust. So if we use slightly different dust attention rho, for instance, the dust attention curve similar to the SMC dust extinction curve, we will find a completely different IRX beta relationship to which provides us a completely different dust attention correction to the stuff to the UV wavelength observations. These authors use local starburst galaxies as an analog of high-resolution galaxies, which typically have an elevated star formation rate compared to local galaxies. However, if these local starbursts are complete analog of high-resolution galaxies or not is still, large assumptions, and we will need to really establish and check this relationship at dust attention property directly using high-resolution galaxies. First, this kind of study already started, and several studies started to show that the dust attention property seems to be different or could be evolved at high-resolution universe. For instance, this Peter K-Pack 2015 showed that the redshift 5.5 galaxies, although relatively small number of galaxy observations, these authors have found that a very low amount of infrared emissions from these redshift 5.5 star-forming galaxies, and showing that the IRX beta relationship of these local starburst galaxies and high-resolution galaxies is completely different. Now, this uncertainty of our understanding of dust attention property is now tightly linked to our uncertainty of our understanding of star formation activity at high redshift. So what we really need to do is with the more large sample size and to confirm this dust attention property at high redshift using the high redshift galaxies themselves. In the Alpine survey, we started to study this dust attention property using relatively large number of galaxies. Just a quick introduction, Alpine survey is an ALMA large program performed in ALMA cycle 5 and ALMA cycle 6. This Alpine uses 118 UV selected main sequence galaxies to observe C2 158 micron emission line and underlying dust continuum. Our galaxies are located at redshift 426, and we selected these galaxies aiming to pick up the very typical galaxy populations at these redshifts, meaning that these galaxies are consistent with the so-called main star-forming main sequence of these high redshift, and we selected these galaxies selected from the very large parameter space in terms of 2 orders of magnitude in stellar mass and 2 orders of magnitude in star formation rate. From these 118 galaxies, we detected the 23 dust continuum individually, like here, and these 23 detection and non-detection are very ideal chance to study the dust attention property using IRX beta relationship. So to analyze IRX beta relationship, we just need to do 2 things. One is using ancillary rest frame UV observations. We first need to measure UV spectral slope and UV luminosity. And the second thing is to estimate infrared luminosity of these galaxies. To do that, we first need to calibrate or create the fine infrared SED from the stacking ancillary harsher images. For creating these stacks are made by the similar sample selection method similar to Alpine survey, and by doing that, we first determined the average fine infrared SED we can apply to these high redshift galaxies we observed. By using these fine infrared SED shape, we estimated infrared luminosity of these high redshift galaxies. Yeah, by this analysis, we created the IRX beta relationship like this. So individual small points are the individual galaxy dust continuum detections, and this downward triangle is the 3 sigma upper limits for dust continuum non-detection cases. And large squares are the stacking analysis combining both detection plus non-detections. So by looking at this figure, we first noted 2 things. One is that apparently these individual detection, also non-detection, and in particular for these stacking analysis shows that the very low IRX or infrared luminosity compared to the local relationship shown by the solid line. Another thing is that a large fraction of this non-detection comes from the extremely blue beta galaxies. These galaxies have sometimes exceeding the UV spectral slope limit of assumed in local galaxies. This limit means that these occurs when the galaxy completely do not have a dust attenuation. So they are completely dust-free and infrared luminosity is consistent with 0. Exceeding this limit means that these galaxies' intrinsic UV spectral slope is much bluer than the local galaxies. So to calculate these high-rested versions of IRX beta relationship, we first assume that bluer UV spectral slope and performed just a simple fitting to the stacking results. And we found a very flat IRX beta relationship, which in turn means a very steep dust attenuation curve, which creates a very red color even when there is only small dust attenuations. This result suggests that if we use the locally calibrated relationship, we would overestimate or overcorrect dust attenuation and overestimate star formation rate of high-rested galaxies, in particular redshift greater than 4. Another way to interpret this result is to look at the obscured fractions of galaxies. Obscured fraction is simply defined by the star formation rate derived by only from the infrared luminosity divided by the total star formation rate. In the previous study, this obscured fraction as a function of stellar mass are completely constant across the redshift range 0 to 2.5, shown by this study by Kate Whitaker 2017, which means that on average, these galaxies falls into the single relationship between obscured fraction versus stellar mass at this redshift range. If we plot our result here, we see in particular for these stacking results, we find very low amount of obscured fractions. For instance, at redshift 5.5 galaxies, we found about 50% of obscured fraction, even for these very massive galaxies. And this 50% is very, very low compared to the about 90% of obscured fractions we previously found by local lower redshift galaxies. So the very naive interpretation is that we are finding or witnessing that the very rapid buildup of dust obscured star formation activity from redshift 6 to redshift around 3. However, another potential interpretation is that we could be biased towards the UV bright galaxy or low obscured fraction galaxies, and we could be missing some very dust obscured galaxies, and meaning that this low obscured fraction could be created by our sample selection bias. So the next second topic of my talk is focusing on this sample selection bias, and I would like to introduce our recent small step to understand this sample selection bias. So far we have been assuming that even when there's the dust attenuation, we assumed that some fraction of UV emission can be observed. However, if there's a heavily dust obscured galaxy exists, almost entire UV wavelengths, UV emissions are dust obscured, and in these cases, we cannot identify galaxy by restrained UV emission and only can observe them by far infrared wavelengths observations. This kind of situation is very common for the very massive, dusty, and also extremely starbursting galaxies. For instance, star formation rate greater than 10 to more than 1,000 solar mass per year. This kind of very dusty galaxies happens or sometimes very bright in infrared and sometimes called submillimeter galaxies. These extremely starburst galaxies are known to be relatively rare in number, in particular for high-redshift galaxies, and could have a very little contribution to the star formation rate density, at least in the very high-redshift universe. However, if this kind of very heavily dust obscured galaxies exist in common in the less extreme population of galaxies, which could be missing, it could mean that we could be missing large fractions of these heavily dust obscured galaxies, because our understanding of these very high-risk galaxies are mostly relying on the UV wavelengths-based galaxy identifications. So now it is very important question, I think, is that if we are really having a complete identification of galaxies from rest frame UV, or our understanding of galaxy identifications is incomplete because they are too our bias to the UV bright galaxies. So indeed, this kind of study are already progressing rapidly recently. For instance, this excellent work by Wang et al. 2019 showed that at restaurant 4, these heavily dust obscured galaxies indeed exist very common in the very massive galaxies. And these galaxies are consistent with main sequence galaxies, meaning that these galaxies are not very extreme starburst galaxies. These galaxies are completely absent in the rest frame UV observations, and these galaxies can be seen starting from rest frame optical or fine infrared wavelengths. However, we still don't know this kind of heavily dust obscure but less extreme galaxy population exists at very high redshift so far, and we are still trying to understand what this kind of population exists or not at high redshift. So recently, our study of this topic has, we are working on this topic using the ongoing Alma-Roj program Rebels. So in short, again, the Rebels survey is an ongoing Alma-Roj program, and in Rebels, we are observing 40 galaxies, 40 very UV bright main sequence galaxies at redshift 6.5 to 9. And we are performing this ALMA scans of C2 158 micron emission line or 388 micron emissions, and also getting the very deep dust continuum emissions. Currently, about 85% of observation has been completed in previous cycle 7, and providing us these excellent data sets for the C2 and dust continuum detections of very high redshift galaxies. From these 40 galaxies, I would like to focus on these two galaxies. One is Rebel 29 and another is Rebel 12. From these observations from the center of the field of view, we detected the C2 emission line and dust continuum from both of these two targets. And so surprisingly, when we were investigating this C2 moment zero map, we also find a very bright some signal slightly offset from the center of the field of view. These two detections are really the detection of additional emission line, clear, and also accompanied with the dust continuum detection at the same time. Surprisingly, completely the same frequency as the central target from both of these two fields, meaning that this emission line does not really comes from some random foreground galaxies, because we just need to have some very like a miraculous cases. However, we think that this is alternatively we interpret this is the companion galaxy of these UV bright galaxies at the physically connected. Interestingly, we didn't find any rest frame UV emission even using very deep observations. For instance, HST observations of this field do not have any detections, or the stacking analysis of near-infrared observation for this field, we didn't find anything in the rest frame UV wavelengths, meaning that these emitters comes from C2 emission comes from the very high redshift, but also comes from the heavily dust obscured galaxies. Although these are heavily dust obscured galaxies, actually this C2 emission line and also the dust continuum is not really extremely bright, or however, but they are very, very consistent with the central galaxies. And this suggests that these heavily dust obscured galaxies are consistent with the galaxy at the main sequence or typical galaxy populations. So we concluded that this is the finding of the heavily dust obscured, but otherwise very, very normal galaxies. They are just faint in Western UV and heavily dust obscured, but otherwise they are very typical galaxies at these redshifts and consistent with the seems likely to be consistent with the main sequence of galaxies at a redshift around 7. So we identified these surprising serendipitous galaxies from from some kind of overdensity around UV bright galaxies. So estimating how much these galaxies contribute to star formation rate density is still unknown. And I hope that the future observations, such as the Large Field ALMA Blank Field Survey or the rest frame optical observation by James Webb, can find more and more these galaxies from random fields or these overdensity regions. So in summary, so because time is approaching, so I would like to summarize here. We have in Alpine survey, we have studied dust attenuation property and obscurity fraction of these high redshift galaxies, around 4 to 6 galaxies. And in the Rebel survey, we started to find these dusty but otherwise normal galaxies at redshift around 7. And yeah, I will stop here and thank you for listening.
Thanks a lot, Yoshi. That was great talk, very nice results. So do we have any questions? I see that indeed we already have 2 questions, maybe 3. So let's start with Paola, which was the first one. Paola, if you want to go ahead, please.
Yeah, hi, hello. Thank you very much for the interesting talk. I have a question. Maybe you said that, maybe I missed it. Have you checked whether there is a possibility that these galaxies have a different kind of dust, which is not what we see in the nearby universe? For instance, larger grains or colder dust?
Yeah. So yeah, in terms of dust temperature, we think that we are having, because we determined average fine infrared ACD from the stacking analysis of similar kind of galaxies. We think that the dust temperature on average are not really special for these high-range galaxies. So probably one interpretation. Yeah. So in the end, actually, we still don't have an answer for that question. I think we still don't know how dust property different at the high redshift, or could be dust geometry is different from the local galaxy, because dust high-res galaxy is typically have very clumpy structure in star-forming regions, and how these clump star-forming molecular gas clump dispersal timescale affect dust distributions around newborn stars are so completely unknown. So this is unfortunately our understanding is purely based on empirical studies.
Okay, I think the second one was Jonathan. Jonathan, do you want to ask your question?
Yes, so thank you for the nice talk. Do you have sensitivity in the rest frame UV extinction to the 2175 angstrom extinction feature?
2175. Yeah, unfortunately for this study, I still didn't analyze these 25. Yeah, these deep in the because although we have plenty of data points, we just our analysis here is based on individual galaxy basis, which does not have really sensitivity to 2175 angstrom.
Right, now you probably need to stack, but
yeah, that would be the best opportunity, and we in this analysis we didn't perform that analysis, but it should be very interesting.
Okay, thank you.
And now we have another question here on Zoom. Hil-sang, please go ahead.
Thanks, Yoshi. Do you hear me, by the way?
Yes, we can hear you.
it's slightly related with the Paula's questions. I understand the motivation of stacking, but I'm looking at your IRX data relationship. The result seems more like consistent with the SMC type, the result. But I was worried a bit about the stacking because you sampled a wide range of stellar masses, which obviously have a different metallicity. So that metallicity heavily depends on dust model, effects of dust model. So can you comment how useful the stacking is to drive the conclusion that the observed IRX data relationship is very different from the local relationship?
Yeah. So yeah, in the stacking analysis, I mean, these large squares, we would like to determine like average kind of dust attenuation properties. And in terms of, so because this stacking has been made by the stacking on the beams on beta, and also we try to stack on the different beam, for instance, beam by stellar mass, but binning by stellar mass gives us some of the relatively known relationship between IRX and stellar mass relationship is really not completely making sense for our sample, and find that very scattered result. So in that sense, this IRX beta relationship stacks is like trying to estimate average relation between dust attenuation and its emission. So this beta we stacked assuming that the beta and IRX is physically connected, which might not be the case for some part of the galaxy, but on average, our results, is assuming that the beta and IRX is physically connected. I'm not sure if I answer your question, sorry.
Yeah, maybe I should just follow your papers. Thank you very much anyway. Thanks.
Thanks. So I think the time is more or less over. So thanks again, Yoshi, for this great talk. And maybe Giacomo, you can go ahead with Giuliana.
Yes, sure. Yes, thank you, Michele, and congratulations, Yoshi, for the great talk. And so now we move to the second speaker of today, who is Giuliana Cosentino. I'm very happy to welcome Giuliana. Giuliana got the PhD in 2019 on the University College of London. She with a thesis on physical and chemical processing cloud collision, so the early stage of star formation. And then she stayed in this field, and she moved to as an Origins Fellow at Chalmers University of Technology. Now, Giuliana told me that you pronounce it Chalmers in Swedish. I hope this is the correct pronunciation for Chalmers. Yes, Giuliana, she's an expert in very early stage of star formation, particularly infrared dark clouds and basically magnetic hydrodynamic shocks. And this is what she's gonna talk to us today. I wanted to say also, Giuliana, I had the pleasure to meet Giuliana when she was at ESO with the ESO studentship, and I would like to take this occasion to advertise that in fact the ESO studentship is a fantastic experience. So Giuliana can confirm it, and we have a new call for application by the end of May. So please, all the PhD students who are already enrolled in a PhD program are all welcome to apply for the ESO studentship. All the information are our recruitment portal, so please go and have a look. And if you need questions, you can contact me or the Office for Science anytime. We will be happy to give you information. Sorry, I took 1 minute for this, but Giuliana, if you're ready, you can. Yes, very good. But we cannot hear you.
Can you hear me now? I haven't.
Perfectly. Yes. So please go ahead and. Yeah,
thank you, Giacomo. Thank you very much for the nice introduction. And if I can say something about the ESO studentship as well, I would say that was one of the best experience of my life. It really is fantastic from a scientific point of view, but also from a human point of view. So I highly recommend it. So today I'm going to show you my work on the interaction between supernova remnants and molecular clouds. I would take the occasion to thank the organizer for giving me the opportunity to present this today. And I also, before starting, would like to say that this has been a work done in collaboration with many scientists from basically, I would say, all over the world. Their names are listed in here, and I would like to thank them very much. Okay, so when we talk about massive star formation and the evolutionary path of massive stars, this is probably the picture that comes to our mind more often. We know that massive stars form in molecular cloud. We know that they at some point become some protostars appear and they clear their surrounding. They become massive stars of main sequence. They live their lives until they die very spectacularly as a supernova explosion, leaving behind either a neutron star or a black hole. Now, from this picture, it may seem that we have all the information that we need, but that's actually not the case. There are several questions still unanswered, and in particular, we don't really have an idea of what is happening in this step. So how do we go from a molecular cloud to a protostar? We don't have yet a clear understanding of a mechanism that is able to gather together large amounts of material in the relatively short time scale of massive star formation. And so we don't really know how massive star formation is emitted in molecular clouds. From an observational point of view, the study of this, trying to understand and answer this question can bring several challenges. So first of all, massive stars are usually born in clusters and not as isolated sources, which means that they are embedded in crowded environments, which makes it very difficult to actually isolate the processes ongoing on a source. They usually are located in environments that show high level of extinctions, of visual extinction. So they are usually embedded in cocoons of dust and gas that makes difficult for us to pierce into these layers and see what's going on in there. Finally, these objects are located very far away from us. Usually the distance are several kiloparsec, which means that we need to have very fine telescopes to be able to look in there. And also they drive very strong stellar feedback in the form of winds or molecular outflows, jets, that affect dramatically the environment in which they're born. So it's also very difficult to understand the initial condition of massive star formation from objects that are already formed, so to trace back the history. One way to circumvent the problem is to look at the environment in which these objects are formed. So several theories suggest that the mechanism that is responsible to init star formation in molecular cloud has to be looked at the formation process of these clouds or at the processes that they undergo during their lifetime. Now, the molecular cloud that have the potential in terms of mass and density to form massive stars are known as infrared dark cloud. IRDCs, which is the acronym, are the denser part of giant molecular clouds, so bigger structure in the interstellar medium, and are called infrared dark clouds because they've been first observed as dark features against the mid-infrared galactic background. For example, in this background image that you look at here, there is a combination of MIPSCAL and glimpse data. We have applied some condensation, some very dark features that are infrared dark clouds. These objects are very cold with temperature below 20 Kelvin. They show high level of extinction, as I said, of 100 of magnitude, and they are very dense. They are density higher than 10 to the 4 centimeter minus 3. Of course, infrared dark clouds can form stars at a wide range of masses, but they are those objects that have the potential to form the IMAST end of star formation, to host the IMAST end of star formation. Among the several theories that have been proposed for the formation of infrared dark clouds, we have cloud collision. This theory suggests that the giant molecular clouds, which has this big structure in which IRDCs are located, are found, these objects can actually orbit around the galactic plane and collide And in this gentle collision, they can shock compress the gas between them, forming very filamentary dense structure that in this simulation from Wu et al. 2017 are seen are very red feature, very dense. These are the newly formed IRDCs. The compression of the gas in there can trigger the formation of massive stars in the newly formed cloud. Another theory suggests that multi-episodic shock compression driven by stellar feedback, so H2 region or supernova remnants on the material in the interstellar medium, so either atomic clouds or already formed molecular clouds, can either assemble the cloud itself, and since these are multiple shock episodes, these can also further process the cloud, compressing the gas and triggering formation of massive stars in there. Now, this is, of course, not a complete, comprehensive list of theories that try to explain the formation of massive stars in infrared clouds or the formation of infrared clouds themselves. But the thing that these two theories have in common is the presence of shocks, interstellar shock, which I'm particularly interested in. Now, shocks have been defined as irreversible pressure-driven fluid dynamical disturbance of the gas in the interstellar medium. We have a solid theory on magnetohydrodynamical shock, and what this theory tells us is that when we assume that the shock cannot evolve in time, so we adopt a non-time dependent treatment, the theory tells us that two kinds of shocks can develop in the interstellar medium. If the shock is very fast, so higher velocity higher than 50 km per second, the gas is heated very suddenly in an almost instantaneous way. And this very sudden heating doesn't allow cooling process to occur at the same time. This causes a jump in the quantity that describes the state of the gas. And indeed, this kind of shock is called J-type shock, which stands for jump-like shock. And it appears as a discontinuity in the quantity that describes the shock and the gas. On the other hand, for shocks that are slower and that propagates in a medium that has a low level of ionization, since the shock is lower, the gas is also heated, but at the same time, cooling process can take place. So creating a balance between cooling and heating effects, so that the quantity that describe the state of the gas change continuously. So what we observe is a dissipation region with a certain length. This is called continuous type shock or C-type shock. If we assume instead a time-dependent treatment of the shock, what theories tell us is that we can have a combination of the two kinds of shock, which are known as CJ-type shock. So these are shocks that start with a J-type discontinuity and then evolve with a shallower discontinuity, with a shallower shock, which is a C-type shock. The point is that usually, even for sufficiently fast shock, the length of this dissipation region is a sub-parsec scale is quite low. This has so far prevented us to actually pierce into the structure and being able to resolve the structure. But I hope that by the end of the talk, you'll be convinced that we actually have some evidence of this. So since we cannot actually look into their structure, how have been shocks detected in space, in the interstellar medium? Well, this shock deeply affect the kinematic structure and line profile and morphology of molecular tracers, whose chemistry is connected to the presence of shocks. One of these is the silicon monoxide, so SiO, which is heavily depleted in quiescent region. The abundance is down to 10 to the minus 12, so it's basically not detected in quiescent regions. But when a shock occurs, SiO, the abundance of SiO can be enhanced up to a factor of 10 to the 6. And this is because when a shock occurs, as we are seeing here, the dust is destroyed, is sputtered. Since the silicon is mostly locked in the core of the dust, the Si is released into the gas phase. It can react with oxygen and form silicon monoxide that we observe in shocked region then. Now, typical regions in which we find shock are star-forming regions due to molecular outflow, basically. These regions, in this region, the emission of the SIO is very compact, seen as a compact emission, a morphologically compact emission around massive cores in which star formation is ongoing. And since the velocity of the shocks are quite high, several tens of kilometers per second, the line profile that we observe in spectra are very broad. On the other hand, in shocks that are either due to cloud-cloud collision or driven by supernova remnants or H2 region, the velocities are expected to be smaller, or the order of 10 kilometers per second, which produce much narrower line profile. At the same time, since the shock is occurring on parsec scales, we also expect the SIO to be widespread on a parsec scale. So we can use, we can look for SIO which is spatially widespread and which has narrow line profile to identify signature of these cloud-cloud collision or larger scale shocks in molecular cloud, in infrared dark clouds. And this is what we have been doing for a sample of cloud selected from the sample of IRDCs in Butler et al. 2009, 2012. So what you're looking at in here, in color scale, is the mass surface density map obtained by Kainulainen et al. In 2013 for the 10 clouds of the sample, year 9. In black contours, we have the SIO emission. The transition is the 2:1, 86.8 gigahertz that we have detected using the IRAN 30-meter telescope. Toward these clouds, we found that cloud E doesn't show any SIO emission. On the other hand, cloud A and cloud I show very interesting SIO emission. That is, they show the emission broad, widespread and narrow SIO emission mixed with the broad and bright SIO emission due to star formation. Now, these clouds are associated with the H2 region. So we have suggested that this widespread and narrow SIO emission may be tracing indeed the interaction with the H2 region or with the flows of gas pushed by this H2 region, but this needs to be confirmed with high resolution data. On a little bit off-topic side, I just would like to say that we have done some work toward cloud C. In here, the SIO is very broad and is clearly associated with ongoing star formation. But toward this cloud, in the same frequency setup that we have used to detect silicon monoxide, we have obtained several tracers, several other molecular tracers. And Negaren Tekabi, which is a master student in our group at Chalmers, has been comparing the abundances of these tracers with those predicted by astrochemical models to be able to infer the physical condition of the cloud. She has recently been accepted for a PhD position in Hertfordshire, and she will be leaving us soon. But the cloud that I would like to talk to you today is actually Cloud G. This cloud, as you can see from here, the SIO emission in black contours is not widespread across the cloud, but is actually located at the edge of the cloud, and the outskirts of the clouds are shown in this magenta contour, which correspond to the 20 magnitude contour of visual extinction in the map. And as you can see, this SIO is actually located in correspondence of a dense ridge in here, and is far off from the massive cores within the cloud, which are the sites in which star formation may be ongoing. We were very excited by these results, and we were even more interested because this emission is actually widespread across a parsec scale, as we were looking for. And moreover, the emission is actually very narrow, because more than 99% of the emission shows a length width that is smaller than 3 kilometers per second. And in any case, there's no emission with the length width higher than 5 kilometers per second. Now, this cloud is actually located in a very dynamical environment. Cloud G is known to be located in between and at the same distance between an H2 region and the supernova remnant W44, with which the cloud is actually interacting, as seen by previous work. So we study further the SIO emission toward this cloud by using ALMA. So As you can see in here, what we are looking here is the cloud in white shadow. This is again the 20 magnitude level. And in orange contours, we see the SIO emission to 1 as well, now seen with ALMA. This is a combination of a 12-meter array and ACA data. And from the orange contour, we already see that the SIO emission seems to be organized into 2 parallel structures that seems to be caught in the act of plunging into the ridge seen in white shadow. If we analyze the kinematics of this SIO gas, which is in this movie, we see that indeed the gas is approaching the cloud from a velocity of roughly 46 kilometers per second, is approaching the cloud, plunging into the ridge, and as soon as it plunges, it starts to decelerate down to a velocity of 38 kilometers per second-ish. If you like, this is what happened. I come from a city that is nearby the sea, so basically this is what happened when you have a wave, a sea wave that approach a sandy shore and breaks. That's how we picture it. We also extract position velocity diagram across the shock to better understand the kinematics of the gas. And what we saw is that this deceleration in the gas is occurring in 2 steps: an almost vertical drop, like a jump, of a couple of kilometers per second, and then a shallower deceleration that is continuously happening toward a length of 15 arc second. This already, like this, for us, that it was resembling the kinematic structure that we saw a few slides ago for a time-dependent CJ-type shock. Hence, we have compared these kinematics with those predicted by models, grid-on models produced with the MHD vote code from Flower and Pinot de Forêt, 2015. And we saw that indeed the kinematic is reproduced by a shock of roughly 22 kilometers per second, plunging into a medium of 10 to the minus 4 centimeter minus 3. This is, at the best of our knowledge, the first time that this internal structure of a CJ-type shock is actually resolved. So this kind of interaction between supernova remnants and molecular cloud can offer great insight to better study our current understanding of MHD theories. We used C18O data obtained with the IRAM 30-meter telescope again. We obtained the 1-to-0 and 2-to-1 transition to study if, to investigate whether there was a density enhancement caused by the shock propagation into the cloud. What we saw is that we extracted 2 spectra off and on shock, and we saw that the gas showed 2 velocity components. The velocity component of 43 kilometers per second is indicative of the pre-shock gas. Indeed, it appears where there's no SIO. And then we have a post-shock component, which is a 40 kilometers per second when the gas has already decelerated. We used RATEC to reproduce the C18O data intensity and ratio. And what we saw is that the density between the pre and post-shock gas is actually, it has been enhanced by a factor of 10. So the final density is, the post-shock density is up to 10 to the 5 centimeter minus 3, which basically is consistent with those expected in the regions of star forming or massive star formation. It needs, of course, to be addressed whether this cloud will effectively form star. But I mean, in this kind of interaction, what we see is that indeed the final density is consistent with the one that is required to form massive stars. Of course, a single object doesn't really make a rule. This is a very interesting result. It is very promising, but we need to find more places in which this is happening. So we have started the ESO public spectroscopic survey called SHREC, which is an acronym that stands for Shock Interaction Between Supernova Remnants and Molecular Cloud. And this project, SHREC, aims to look to a sample of 27 supernova remnants. These are only few of the sample. What we will do basically, we will use we have been actually using, because the project is ongoing, the 12-meter antenna at the Arizona Radio Observatory to map silicon monoxide emission and dense gas tracers toward this sample of 27 supernova remnants, which have been selected for showing at least one observational signature of interaction with molecular clouds. This will bring us to have mapped more or less 160 regions around supernova remnants, and the map is 10 by 10 arc minutes. The project in total will be 800 hours, and we are using the AROS receiver with a bandwidth of 500 megahertz, which give us a resolution of 0.3 kilometer per second, and allow us also to detect not just SIO, but also H13CO+ and HN13C, which are typical tracers of dense gas. Some of the SHREC objectives are this is an exploratory project which aims to find the places in which this interaction is ongoing. And the strength is that we can map large areas in an efficient time. We will study the gas kinematics of both the shocked and dense gas. And also we would like to estimate, to the best of the possibility, the momentum that is injected from the supernova into the molecular phase of the interstellar medium, because this can be actually important for the regulation on large scale of star formation efficiency in galaxy. Now, SHREC is a large family. It involves scientists from many institutes all over the world, and scientists are taking part from carrying over observations for data interpretation and so on. And something that I would like to point out is that the observation for SHREC and in general with the Arizona Radio Observatory are a very useful tool to train a new generation of scientists, I would say, that are interested in radio observations. This is because the observation can be done remotely, and usually you have on the other side a super skilled operator that is maneuvering the telescope. So the PI or scientists in general are required to prepare the observing plan, to have a strategy, of course, but there's this great interaction with the operator that enriches you in a fantastic way. So if you're interested to have students taking up a SHREC observing shift, please drop me an email, because this is a great opportunity, even for people that have absolutely no experience with observations. Finally, I would like to show you some of the results that we have been obtaining, some maps. We have observed, for example, IC443, which is a very well-known supernova remnants, here seen in the WISL sky survey image. We have detected SIO 221, H13CO+, and the HN13C seems to be not detected, probably below the sensitivity limit. And then we have detected the SIO emission toward the W41, which is another interesting supernova, known to be interacting with a molecular cloud over here. So this is the glimpse image in the background. This is the TOR continuum from the TOR surveys. And in yellow and cyan contours are the SIO that we have detected. Before leaving you, I just would like to say that SHREC is definitely the most important ongoing project that we have. But at the same time, we are doing, we have several work in progress projects toward mainly Cloud G, which was the first candidate, the first source in which we identify this kind of interaction. We have these are all accepted proposal, at least these are ALMA and ALMA Apex of the dense gas emissions, CO multi-J transition, and the 3 millimeter line survey are already observed. We are trying to extend this work also to the supernovae that we detect SIO 221 with SHREC. So we are trying to extend all this work to IC443 and W41, and most of these proposals have been already accepted or observed already. And I will leave you with my summary, and I would like to thank you very much for joining and attending the talk.
Thank you very much, Giuliana. Thank you for the great talk. Congratulations for the impressive amount of work. And so before starting, we have 5 minutes for questions, more or less. So of course, people in the chat from YouTube, they can post a question on the chat, while people on Zoom, they are welcome to raise the hand if they have questions anytime. For the moment, I see no hands, and so I will start myself, Giuliana, so I'm really fascinated by this, and I am particularly interested in an aspect that maybe is a bit on the side with respect to what you're really looking into the physical processes, because with Gaia, we start to detect huge filamentary structures, basically of the size of 200 parsecs, of coeval stars that we suspect they are basically the relict of filamentary star formations, basically. Now, honestly, this is what we observe, but I personally have no idea really how this can happen. So how can you have molecular clouds, okay, and having a coherent formation, instantaneous formation at the same time on a physical size of 200 parsec? So
I guess this is the if I have like on top of my mind to answer the question, I would say what occurs is that these shocks can develop on the parsec scale, so they can be like very extended. It's parsec scale on cloud G, for example, but there's no reason why they could not be more like extended, especially if I think of it driven by a supernova.
But exactly. But my question would be, because really I don't know. So when you at the beginning you show the 2 scenarios, right? Collision of clouds or supernova triggered star formation, basically. But do you think so? In a physical scale, so do they differ? So they differ the physical state to which this can happen. So what I mean, I would imagine that if you have a cloud collision, this can take up to several hundred parsec scale, depending on the size of the molecular cloud. What I guess a supernova, I don't know, the effect, is it the shock affects a smaller physical,
Yes, probably the shock effect that you have in a supernova is slightly, I would expect to involve a smaller physical scale, but there's also due to the fact that the gas around the supernova may not be the same everywhere, so there could be, the people have seen that the material around supernova remnants is clumpy and not, so it's not like a perfect ring around the shell, no? So this can be more local with respect to cloud-cloud collision, in which you have the collision of on the scale of the GM molecular cloud, which can be more extended. So yeah.
I see. Thank you. So there is actually a question from the chat. I see a hand. Dietrich, please go ahead.
Yeah, thank you. This was a very nice talk, very, very clear. And also your interpretation of the breaking wave is quite convincing. Still, I have a question about it. Could it also be, or you must have excluded the possibility that this is due to a geometrical effect, that there's a different angle with respect to the plane of the sky?
In terms of land width?
In terms of the apparent deceleration, you could have a lower velocity just as a result of a different direction of the expansion with respect to the plane of the sky, just as a simple geometric effect.
There could be, but we are seeing the same effect, very similar effect, for example, toward the IC443. The gas is doing something very similar. We see this velocity gradient across the gas. This is a work in progress, of course. So it seems very unlikely that to source we have the same, geometrical effect. And we are also exploring other molecular traces that may to see how they compare with this gas, with this shocked gas. And we have in particularly looked at the dense gas traces like N2H plus and H13CO plus with ALMA. That's also a work in progress. And we actually see this dense gas appeared as at the far at like 38 kilometers per second as a shock compressed layer. So it seems quite unlikely there is a projection effect, or purely a projection effect, I would say.
Yeah, sounds very convincing. Thank you.
Thank you.
Thank you very much. So also, Giuliana, we have another question, maybe the final one, because we are running out of time, unfortunately. But we have a question which we received by email, so that's why I'm using the phone. So one of the cases. So it's sorry, I'm gonna turn my head just because I'm watching the.
No problem.
Right, sorry about that. So so Izasco Jimenez Sierra, this is the name of the person, asks, how common do you think these large-scale cloud-cloud interactions are? And could you say something already from your IRAM 30-meter observation sample?
I'm sorry, can you repeat the first part of the question?
So how common do you think that these cloud-cloud collisions, so that these large-scale cloud-cloud interactions are? So how common they are, and if you can detect them already?
In the 10 cloud sample that we have studied from, there is the sample presented in Butler et al. Of the 10 clouds, we see pure cloud-cloud collision in cloud H, which Izasco has led work on, and several tracers have highlighted the presence of cloud-cloud collision in there. In the 10 cloud sample, we don't really see evidence of cloud-cloud collision in other clouds, but this could be due, for example, also to the fact that the star formation activity in the clouds is more evolved and is a later stage, and it has already affected. So the bright component of the SIO has taken over and has completely obscured the narrow SIO. That's why it's important to look at stars that have really low level of star formation activity. So the other clouds in which we see narrow and widespread SIO emission are all associated with the stellar feedback, so either H2 region or supernova remnants. There are several work, although, from mainly people based in Japan, actually, that have produced extensive work on cloud-cloud collision in single sources. So they may be not as common as we would like, probably, but they are definitely a process to take into account. And for example, the multi-episodic shock and compression theory also predict the presence of a cloud-cloud collision, although as a secondary effect of this displacement of big flows in the interstellar medium.
Okay, good. I think this answers the question. So with this, we can close the colloquium of today, and I would like to thank Giuliana again for the talk, and also Michele Yoshi for the talks and chairing the session. Of course, there are a lot of claps around, as I can see. So congratulations for being with us, and to everyone, thank you very much for coming and for attending the event. And so we will be back with the Hypatia Colloquium again the next Tuesday. Please keep following us, and you can also keep, just to remind you that the video is staying on YouTube, so you can watch it later. And also, if you go to our program pages, you can click on the title of the talks, and you can download the curriculum vitae of our speakers, so you can meet them more closely and know about them a bit more. So with this, I would like to thank everyone, and see you next week. Thank you again.
Thank you.